Now we move on to the third and final phase of urine formation, which is water conservation in the collecting duct. As we know already, the kidney is involved in eliminating metabolic waste, but not only does it eliminate wet metabolic wastes, it's important in preventing excessive water loss. So as the kidney returns water to the tissue fluid in the bloodstream, the remaining fluid in the tubule is going to pass as urine. As it passes through the collecting duct, it becomes more concentrated as water is removed from the fluid. So the collecting duct begins in the cortex. And in the cortex, the fluid in the collecting duct is isoosmotic to the blood in the blood vessels. As it passes down from the cortex into the medulla, it's going to reabsorb water into the tissues and thus concentrate urine. It's going to get concentrated up to 4 times. The medullary portion of the collecting duct is much more permeable to water than sodium chloride, so the water passes out. As fluid moves down through the collecting duct, it moves into surrounding tissue that has higher and higher osmolarity, and so more and more water is drawn out of the duct back into the tissues, and as we'll see, it goes back into the blood circulation. The concentration of urine is dependent on the body's state of hydration. When someone is very hydrated, we'll see water diuresis. It's going to produce a large volume of hypotonic urine, meaning there's less solutes in it, much lighter in color. In this case, the cortical portion of the collecting duct is going to reabsorb sodium chloride, but it's impermeable to water, and thus water will remain in the urine, creating this hypotonic solution. In the case of dehydration, we'll see production of hypertonic urine. The high blood osmolarity is going to stimulate release of antidiuretic hormone from the posterior pituitary, and this hormone increases the permeability of the epithelial cells because it causes them to synthesize more aquaporin channels. With more aquaporin channels, you can have more transcellular transport of water by the renal tubule cells, drawing water back into the tissues and eventually back into the blood. So you're going to see that the urine is much more concentrated and more water is being held onto by the collecting duct. When blood pressure is very low, like in a dehydrated person, the glomerular filtration rate is also going to be low. Thus, the filtrate is going to move much more slowly through the collecting duct, leaving much more time for reabsorption. We'll see that more salt is removed in that time, and thus more water is reabsorbed, and again, less urine is produced. The question now is, how does the kidney tubule continue to conserve water, retain water? And this lies in this countercurrent multiplier effect. The renal medulla is 4 times as salty, solute dense, than the cortex. And so as water descends down through the tubule, it becomes less and less hydrated. The osmotic draw becomes more and more to pull the water out of the tubule. The nephron loop acts as a countercurrent multiplier. It's a multiplier because it's continually recapturing salt and returning it to the extracellular fluid of the medulla outside the tubule. And that's going to multiply the salinity in the adrenal medulla. It's called countercurrent because the fluid is flowing in opposite directions in adjacent tubules. So fluid flowing down through the descending limb is going to pass through an environment of increasing osmolarity. Most of the descending limb is very, very permeable to water, but not to sodium chloride, and so it favors water moving out of the tubules into the extracellular fluid. Concentrations in the tubular fluid as it drops down and loses water at the bottom end of the loop become about 1200 milliosmolar. Now fluid flowing up through the ascending loop is not permeable to water, and it's actively transporting sodium, potassium, and chloride out through the thick portion of the tubule. That's going to maintain the high osmolarity out in the extracellular fluid of the renal medulla. The tubular fluid is now becoming hypotonic, about 100 milliosmolar, at the top of the loop here. In addition to the solutes being drawn out into the medulla, at the very tip of the loop, the lower end, we're going to see recycling of urea. So urea is going to contribute to the osmolarity in this deep area of the loop as it's collected from the collecting duct, which we'll see here soon. So now let's look at the blood supply in the renal medulla. Obviously, this is a very metabolically active area, and to meet its metabolic needs, the renal medulla needs a good blood supply. However, wouldn't that risk having all of this solute concentration diffuse into the blood and just be carried back into the system through the blood rather than leaving as urine? But as it happens, the blood in the capillaries, in the vasa recta, has its own countercurrent system. So that when it dips down into the medulla, yes, we are losing water into the surround, and we are picking up solutes that are dissolved in the extracellular fluid. However, as the capillaries ascend back up through the medulla, the opposite is occurring. Water is diffusing in as the solute concentration is now greater in the blood, and sodium, chloride, other solutes are diffusing back out. And after it's all said and done, we actually see that much more water leaves in the capillary blood supply, that which was reabsorbed from the nephron loop. So much more water is actually leaving in the vasa recta and re-entering the central blood supply. So this figure gives us a great review of all three parts of urine formation, starting with the glomerular filtrate formation, reabsorption and secretion, and the final stage of water conservation. This will be a really good figure to begin from for putting together your diagramming assignment on the kidneys. Following the slide, we have a short animation showing how the various transport of solutes in and out of the tubule help with water retention.
One of the primary functions of the kidney is better understood at the level of the nephron. In forming urine, the nephron functions to remove metabolic wastes from blood while regulating the volume and composition of body fluids. Urine formation begins in the renal corpuscle, where blood passing through the glomerulus is filtered. Filtrates include water, ions, and other solutes, which are filtered out of the blood and into the capsular space to begin urine formation. Urine passes into the proximal convoluted tubule, then into the nephron loop. The nephron concentrates urine by the process of the countercurrent multiplication system. The countercurrent multiplication system is basically the means by which water and sodium are extracted from the filtrate as it passes through the tubules toward the collecting ducts. This system is called countercurrent because of the dynamics set up by the hairpin turn of the loop of Henle. The direction of flow in the descending limb of the loop is opposite from the direction of flow in the ascending limb. By flowing in opposite directions in such close proximity, a unique interaction occurs. The loop of Henle dips from the cortex of the kidney into the medulla and is surrounded by the medullary interstitial fluid. The countercurrent multiplication system is responsible for not only elevating the concentration of urine in the loop, but more importantly, it elevates the concentration of the interstitial fluid as well. To explain the countercurrent multiplication system, we must first imagine the loop filled with a stationary column of glomerular fluid, which includes water, salt, and urea. At first, the concentration of the glomerular fluid and the surrounding interstitial fluid will be equal at an osmolarity of 300 milliosmoles. Within the walls of the thick segment of the ascending limb, special pumps extract salt, sodium chloride, from the fluid and transport it to the interstitium. The two areas no longer have an equal osmotic pressure, and a gradient has been established. Within the thick segment, the concentration is at 200 milliosmoles, whereas in the medullary tissue, the concentration is at 400 milliosmoles. Over time, a net diffusion of salt into the descending limb and a net diffusion of water out of the descending limb results in a balance in osmolarity between the descending limb and the surrounding interstitium. Because the thick segment is still actively pumping out salt, the osmolarity of the ascending limb is still 200 milliosmoles, and the interstitium and descending limb are balanced at 400. Salt accumulates in the medulla while water is drawn out of the fluid in the descending limb. Water is removed by the vasa recta, which are capillaries that surround the loops. In real life, operation of this gradient occurs while the fluid is flowing. Fluid flowing in from the proximal tubule and out to the distal tubule along with the constant pumping of salt into the medulla contributes to the multiplication of this gradient. As fluid follows the path of the loop, an increasing amount of water is extracted as it reaches the bottom, and an increasing amount of salt is pumped out as the fluid reaches the top. The more salt pumped out, the higher the concentration in the medulla. The higher the concentration in the medulla, the more water is extracted. Eventually, the levels of osmotic pressure are equal horizontally, with the highest value being at the tip of the loop. This level is at 1,400 milliosmoles per liter, which is also the value of the maximal osmolarity of excreted urine. As you can see, fluid becomes more concentrated as it rounds the loop, but it immediately becomes rediluted as it reaches the top. Final concentration of the fluid occurs in the collecting ducts as it must travel back through the concentrated interstitium of the medulla on its way to the calyces. Urine is concentrated even further in the collecting ducts. The collecting duct must transport urine back through the concentration gradient formed by the nephron loop. The walls of the collecting duct are permeable to water, but not to salt. Therefore, an increasing amount of water is drawn out by osmosis as the fluid travels through the gradient. The gradient provides the force for the concentration of urine, but the rate is determined by the amount of antidiuretic hormone, ADH, in the blood. An increase in ADH in the blood causes the collecting ducts to become more permeable to water. Less urine is secreted and it is more concentrated. A decrease in ADH results in a decrease in water removed, thus a larger volume of more dilute urine is excreted.
Okay, so now we've completed the third portion of urine formation, and you're ready to go on and do the Learn Smart module and Connect.